Hello and welcome to Wherobots. My name is Matt Forrest, and today we are going to kick off a series of notebooks that help you get familiarized with our platform, Wherobots Cloud. Now, if you're watching this, you're probably watching this either on our YouTube channel or potentially you're already in the notebook itself, which also has this video. So if you're there already, great. You skipped a few steps ahead. For those of you on the platform, if you want to go ahead and get started, we'll show you those steps now. So if you haven't signed up for an account yet, you can go to wherobots.com. Just head over here to try Wherobots and you can get signed up here. You can either do that on our cloud platform, or if you have an AWS account, you can do that through the AWS marketplace here. So go through those steps and complete your account. You'll have to fill out some information and then get a code through your email. But once you're all set, you can just go ahead and go back here and click sign in, where you'll be prompted to log into the Wherobots Cloud platform. Now, once you are there, if you're on a community edition, you'll see the ability to spin up this tiny instance, or if you're on a pro instance, you'll see all of these other instances available. All you need to do is create a new notebook to get started. So to do that, you just select the runtime. All you need is the tiny runtime to actually run this, and go ahead and click start. That will start the runtime, which you'll see populating down here. And once that's ready, all you have to do is click open, and the notebook service will open up for you. Now, once you've opened up the notebook itself, you can navigate here on the folder. You can open up the onboarding folder here, which you should see. And then you're just going to open up this notebook here, which is the Wherobots onboarding part 1. And we're going to show you how to load some data. So now that we're all caught up, we'll take a look at the notebook here. We're going to do a few different things, loading a few different sample data sets, and actually allow you to interact with some of the functionality in Wherobots. So as the notebook describes here, the things that you're going to do is you're going to load some raster and vector data sets. If it's your first time working with geospatial data, vector data is basically tabular data with a geometric object tied to it, being a point, line, or polygon. A polygon being like a building, a line like a road or a river, and a point, well, like a point. And a raster data set is some sort of imagery or derived imagery. The imagery we'll be working with today is provided by the City of New York Public Data, and that is a 1-foot resolution digital elevation model, which basically gives you the elevation inside a square of 1 foot. Now, raster data sets are basically images, so they'll be TIFFs or some sort of derivative file type like that, and we'll be using that in our example today. So once we do that, we'll actually do a few different things. We'll take a look at those data sets. We'll collect some values from the different data them and showcase what they look like. We'll actually do that both with the Python structure, using some of the data frame Python structures that come with Apache Sedona, which is the library that powers Wherobots Cloud, as well as running some different functions to do zonal statistics, which we'll talk a little bit about later. But this gives you a high-level view of what we're doing here. If you are already in Notebook, you may have loaded this, but this is just the video you're watching right now. So if you need this video here to reference, you can do that as well. So let's go ahead and jump into step 1. So the first step is, if you are loading some of your own data, you need to choose where that data comes from. Now, the best place to load your data is in a cloud storage service like AWS S3. So before we begin, you have to choose kind of where you want to use your storage. Now, you don't have to do anything to run the rest of this notebook today, but just in general, if you want to continue using the platform after this notebook, you need to decide, do you want to use your own S3 bucket, AWS S3 storage bucket, or do you want to use Wherobots managed storage? If you want to use your own, you can connect those files in with the proper permissioning. We'll talk about creating an Iceberg, Apache Iceberg catalog in your own storage in a later version. That's a little bit beyond what we have time for today. Or you can use Wherobots managed cloud. Now, everyone gets access to their own storage. So if you click into the Wherobots Cloud service here, click into storage, and then you can click into this folder data, and you should see your unique customer ID here. This will allow you to upload data to this folder. So you can do that 2 ways. You can just upload a single file, or you can get ingestion credentials here. These will be accessible to you for an hour. So you can upload this with Python, with the command line, anything you want to do there. So basically you get access to your own S3 bucket, and the permissions are already set up so that you can use it in your own bucket. So if you want to do that, there's that. You also have a link here to get more information about how to do that, and basically everything I already covered here. So for our second step, we actually have to connect our notebook down to the compute service. And to do that, we'll set up a Sedona context. So this what describes the steps here. It's pretty simple. We'll import it from the Apache Sedona library. We'll basically create that configuration here. This is similar to a Spark configuration. If you work with Apache Spark, you can add in different options here should you choose. Otherwise, you just need this one line of code to create the configuration, and then you create your Sedona context here. So once we have that ready, we'll create our Sedona context. That's going to connect our notebook down to the compute service that you started up in that first step. And once that return's completed, you'll see that highlight cell here. It should be number 1 if this is your first time running that. The star will go away, and then that should be ready to go. Once that's ready to go, we can move on to our next step. This should take a few seconds, and then you'll be ready to move on. So now that we're into step 3, we're going to load our geospatial data into a Sedona data frame. And that's our first step here. We're going to be loading a GeoParquet file. This file, information about buildings and building footprints in New York City. So you can see the structure of the process that we'll be going through. First, we're going to define our data frame and then read it in using the format GeoParquet. GeoParquet is a similar file type to Parquet, but has geospatial data support in it. And then we're going to load it from that specific location here. Then a few different commands that are good to know is print schema. That will show you the schema of the data set you've just loaded in. Show will show you the first 20 rows. And if you want to limit it to 5 or 15 or however many rows, you can just pass in a number to do that here. So we have some data here that we've defined. This is our New York City file here. That's in our example data. As you can see, we're defining it from an S3 URL endpoint. Going back to step 1, that's why you want to define where you're going to store your data. We have some data loaded up here for you already, and we can go ahead and run this, and we should get our data set back here. So what we can see here is now we have this buildings object, which contains our data. So a few things, like I said, you can run. You can run buildings, dot show, and that will show you the first 20 rows of data. We can explore kind of the data set that's in here that we can get access to. So there's a lot of information about the building type. Is it a commercial, entertainment? Most importantly, the polygon here that you can see is that there's actually a geometric object tied to that and a few other properties as well. Print schema will show you the schema of the data set here. So you can see here, this is the building ID. These are some of the classes that are tied to that, and then some other information about it as well, namely the height, which we'll be using to visualize our data here in a second. The last one that you can do is you can also get the count, a number of rows, just by running count.count, and then parentheses. There's about 8,700 buildings in this data set. It comes from a much larger data set for the entire US, about 130 million individual buildings in the United States, but we just pulled the sample for the island of Manhattan, for at least for this notebook. So in step 4, just like we loaded a vector data set, we can also load a raster data set or an imagery derived data set. Now, what I love about Wherobots is it allows me to seamlessly create 2 data frame objects. One is raster, one in vector, and work alongside of them using the same coding language. There's really not another place that you can do something so seamlessly at scale. So this is what a really nice attribute of Wherobots Cloud is, that I can do this here. So just like we define our path in S3 here. We load it in. Instead of using Python, this time we're going to use SQL. There's a function called rs from path, which will load in, and we'll define that as our raster path to the raster object itself. Just like before, we can do print schema or show. And if you want to do this through a Python structure, you can do that here. So you load in your raster path, you drop some of the extra content that comes with it, and then use that function rs from path to create that new point to that raster data set itself. So here we go again. We'll load in that S3 data set. As you can see here, this is a elevation data set for elevation data in Central Park. Each pixel represents a 1 foot square in the city. So that's what that is. It's a very granular raster data set. And as you can see here, I'm defining my elevation file just like this. We'll pull that in, and now I have my elevation file that I can access. You can do some of the similar things like you did before. You can do print schema and see what the schema is. It's basically going to be the raster data set itself. You can do a count of the number of rows. Oop, that won't work. And you'll see that it's one row. Basically, we're pointing to a single raster data set here. So that raster data set is the row in this case. So it's not as interesting to look at from a tabular perspective, but we'll be able to do some really cool stuff with it. Now I'm going to do one extra step here, which is known as creating a temporary view. Now, so far I've only loaded data into data frames. That data frame is effectively like a temporary object. If I want to use it in the context of Spatial SQL or Sedona SQL, what I need to do is actually create a temporary view, just like you would in a database. Now, it's no data movement. You don't have to move anything around. You're just kind of creating that reference point in memory. As you can see here, what I can do is call it with the elevation data frame, and this function create or replace temporary view. I'm just going to use the same name. You can change the name if you really want to, but it'll create a temporary view for that period, and then you'll be able to use it in a SQL function just like this. So you have this SQL function select star from elevation, where height is above that. That's a fake SQL query, but it gives you the idea of what you can do. So let's go ahead and create that reference point, and now we have that. So that brings us to step 5. Now, if you're not familiar with Central Park, there's a little corner of Strawberry Fields dedicated to the famous artist John Lennon. And what we can do is actually take the latitude and longitude for that location, which is listed here, and write a simple SQL query to get the elevation at that point. So this is the SQL query that we'll run. There's an explanation of all the different steps down here. We're using rs value. Now, rs value is a function that says, given a raster data set, give me the value of the pixel at this specific point location, right? This is a point infinitely small, so that it falls within a single pixel in that space. So we're passing that entire raster. As you see here, we defined this is rs path as rast. So that's our column in our table there, as it were. And then we'll get the elevation in feet from elevation. So that's what we'll do here. And we'll run our query to get the actual execute the query there. I'll go ahead and do that, and then I'll call that function here strawberryfields.show, which will show the result of that data frame. That will actually execute the query. If I'm just here, I'm just defining the query itself. I'm not actually executing anything. And then here I'm actually executing that, and you can see here it got me the elevation in feet, which is at that specific point it's 90 feet above sea level. So it's New York's an island. It's not that high up in the air. So. Okay, so from here, we also want to, of course, visualize some data now. Wherobots is a computational platform to perform spatial analytics and spatial processing. But of course, at some point, you probably want to see your data on a map. So that's what we're going to do here. We have a library called Sedona Kepler, which is based on the open source Kepler GL library that allows us to create map dashboards in the context of a notebook itself. It's a pretty simple sort of structure here. I'm going to show you, and I have a predefined map configuration file, so you don't have to do any of the styling. You can edit it if you want to. But just to help you move through Notebook a little bit faster, we set that up for you in this case. So the code that you need to create is you need to create your map here, which is map. First, import your library, just as you see on this line here. You'll create your map, and then you'll add a data frame here. Now, I've added this configuration file here just to show you like a very simple configuration. The one we have has a lot more complexity to it, just because I styled it and then just pulled the code itself. But you don't have to have that configuration file. You can certainly run it without, and then you would just be styling it using the point and click interface from there. So basically what I did, I just imported some code to open up that JSON configuration and pass that into the map creation function here. So I've imported JSON, which is this line, imported Sedona Kepler here, loaded in that JSON file here, and then I'm going to create my map with the proper configuration. As you can see here, I'm going to add the data frame. There's 3 components, arguments to this function. There's the map itself, which we created on the line above, the buildings, which is the data frame that we established above, and just a layer name, which is NYC buildings. And then this will just return the map for us itself. So we'll go ahead and run that. And what we should get back is a very nice looking map that shows a few different things, which we can break down in a minute here. Okay, so here is the map itself. I've done a few different things with this map, which is basically add a height to the buildings. So each of these buildings has a height attribute, as you can see here. It's actually rendering the height of those buildings itself. So you can see here, you can see where there's the taller or lower buildings in Manhattan. And then I'm also styled them using a specific color here as well. So if we open up the value here, you can see that there's some different values to these. So we have the aviation, banks, colleges, universities, community centers, things like that. Oops. And I think a lot of these are probably residential as well. So we should see some residential buildings down here, but there's a lot of different values you can see in terms of the types of different buildings. So you can kind of see what that looks like. We have this Midtown Manhattan here is a lot of orange, which is going to be professional technical services and some other different things like that. So you can kind of see these are office, residential, and a few other things here, probably like looks like it's a religious building, and then you have some other ones here. So a lot of different kind of categories, but this just gives you a sense of how you can see your actual data on a map. If you want to change that, you can edit that here. So there's a points layer here as well if you wanted to render that. And then you can edit all the options here. There's full support in the documentation that talks about how you can create maps with this as well. Okay, so to bring everything together, let's do a quick analysis using these 2 data sets. What we want to do is there are a few buildings here in Central Park. So there's a few very small buildings that you can see here, as well as a few large ones. I believe this is the Met, I believe. It's one of the museums. I think it's the Met. And you can actually get the elevation of these different buildings doing what we call zonal statistics. So this is the function we'll run. There's a full explanation of the function here below, but just as a brief overview of what zonal statistics is, imagine we have a polygon, in this case a building footprint, and a raster data set below that which has pixels. The zonal statistics will say for every pixel that intersects that building footprint, we'll turn a statistical measure from that. That might be the maximum elevation, that might be the minimum elevation, that might be the standard deviation. In this case, we're just going to return the mean or the average. So the 2 data sets that we've been working with, our elevation data set, which is the DEM, and then the buildings, which is the buildings in Manhattan. We're going to have to do a coordinate transformation as a second step. So the So New York City publishes all of their data in imperial measurements like feet, inches, things like that. To do that, they use this New York State Plano projection. I believe it's the Long Island one that references at this projection number 2263. Now, if you're not familiar with map projections, it's just different ways to represent spatial data or take data from a circular globe and flatten it out. We're going to move it to 4326, which is just a different measurement system used to render web maps. So we'll call this function zonal statistics. We'll pass in the raster input here, which is that same file that same data frame we've been using. We'll pass in the vector geometry, which is all of those building footprints that we have. We'll give it the band. There's only one band in this raster image, so we're just going to pass the value of 1. Within rasters, sometimes there's multiple bands, especially from satellite imagery. So if you think of like an image, you generally have a red, green, blue band. Some of them have up to 20 that detect lots of different things that we can get into another time. But at least for this data set, it's a one band data set, only elevation, that's it. We'll pass the statistic, which is going to be the mean, and we'll ignore the no data columns. And there are some columns in here that have no data tied to them. So we'll just ignore those for the time being. And then what we want to do is pass a spatial predicate. Since we have buildings all over Manhattan, we only care about the ones that touch Central Park. So one of the first things we can do to improve our query speed is say, hey, use this rs intersects function to say, only evaluate the buildings that intersect that raster data set and ignore everything else. So it very quickly gets rid of all of the other data. This really matters, especially when you scale up to another level of performance. The interesting thing about it is that when you look at Wherobots Cloud, we've optimized our individual compute nodes, the actual processing that runs this, to work with spatial data much more efficiently. This is one way you can actually take better advantage of that and get speed performance boosts up to 20 to 60 times compared to what you would using Sedona in any other Spark environment. So with that said, we do our aggregation. We're just going to group that by the property address. So we have an address of that property, and then get rid of any values where there's 0. There's a few no data values that showed up, so I'm just going to ignore those. And then that's what we get. So first things first, I have to create that temporary view of my buildings data frame, which I've done here. Just to confirm, we can see that we have the SRID of that raster data set, which we already know is 2263. So this is just a quick query that can show you what that looks like. So I've created basically 2 queries here. This is contained in a CTE. I'm going to select the building's property address and pass that and give it an alias of name, the actual geometry of the building so we can put it on a map, and then our zonal statistics function. So what this allows me to do is get the average across. So now we have our zonal statistics function, which I said has a few different arguments that it takes. First, the raster data set here. We're going to transform that geometry in the middle step here. So turn it from buildings, the geometry of the buildings, from 4326 into 2263, so we can evaluate that a little bit better. The band of 1, we're going to evaluate the mean, and we're going to ignore the null data. From there, we're going to pass it. We're using the buildings data set and joining it to the elevation data set on this spatial predicate, which is the intersection of the raster and the vector data set, once again transformed here so we can see it there. And then at the end, I'm just going to exclude any values that have 0, so we can just ignore those for the time being. So go ahead and run that, and then we can just see the results here. We'll use that .show call and quickly get the results back from that statistics function. Okay, so now that's completed, you can see here that we have all of our results, and you can see some of these different buildings kind of vary between 95 feet, this one's really low, 18 feet, all the way up to 115, at least for the first 20 rows. And of course, we probably want to put that on a map, so let's go ahead and do the same thing we've done before, put all of our data on a map here. And once again, we have our configuration file set up for you, at least in this case, so you can see all of the data here. And once that's on the map, we'll kind of see the different heights of the buildings and see how that checks out. Okay, so we have all of our data loaded up here, and you can see that if we open up our legend, you can see the lower buildings are going to be in the darker shades here, and the lighter buildings are going to be in the higher buildings are going to be in lighter shades. You can see here, this building is at about 81 feet of elevation, and just to confirm, that is, in fact, yes, it's the Metropolitan Museum of Art, which is this big building here. So you can see that building. You can see some of the other buildings located here as well. So you see some of these basically probably park buildings along here at some of the higher elevations, and some of these at the much lower elevations near the ponds and things like that. Central Park is kind of strange. It's one of the, you think of Manhattan, it's mostly flat, but it's one of the areas that still has some of the original topology of the city. So you get some of these very high areas and very lying areas as well. So that's something interesting there. But that gives you a basic idea of what you can do combining raster and vector data, loading those together, and then some of the functionality that you can use to combine them and perform some, basic spatial analysis like this. So if you want to try some different steps, there's ideas for some different steps that you can do here using different spatial SQL functions and things like that. You can combine and experiment with different data sources. If you are primarily working with raster data, you can do things like an NDVI analysis, and you can also use Overture Maps data, provided some building footprints that we use in this data set here, and you can actually do further analysis with global geospatial data. That data set's already loaded up into Wherobots, and you can get some more information on that using this link. You can try some of the different analytical functions here, creating buffers or doing other spatial analysis functions. You can see a full function reference for Apache Sedona here to get that checking out to see what you can do within the context of a Wherobots notebook. And then there's some other ideas for what we'll be doing in the next series. So if you finish this one, we'll be having some additional notebooks here. The next one will be doing some more advanced vector data loading to look at different data sets you can load in, different data types, file types, things like that, and some of the different spatial functionality you can use with that. And we'll also take a look at how we can load in different raster data sets that maybe we don't even store in our own storage that connect to remote raster data sets that are stored at much higher volumes, global volumes, and things like that. So we'll take a look at that as well. We'll also get some prep for doing spatial joins, which is basically joining data based on their spatial overlap, very similar to what we did today, but even at larger scales than that. So that covers this note for today. If you have any questions, go ahead and drop them in a notebook. You can always email us at support@wherobots.com. Hope you enjoyed this, and yeah, we'll see you in the next tutorial.